And maybe I will begin with getting this kind of picture ready and set up. And so let's get started with a quick summary of what we covered already. And we didn't get, unfortunately, too far. So we've got a lot here to cover to wrap up this chapter today. So I'm just hoping really to get through the material and maybe one or two examples, I hope. But I think the examples will probably have to wait and flow into Thursday. But here's what we have done so far. We started, of course, with the vocabulary, magnets, North Pole, South Pole, like poles repelling each other, unlike poles attracting each other. But when it was all said and done, after a discussion here, we came up with this. And so let me put this on the board. If I were to take a piece of iron, a bar magnet, and I don't even think I even brought a bar magnet out here today. No, I didn't. But if you remember from last time, the bar magnet, where, say, one end we labeled as a North Pole and the other end we labeled as a South Pole, one of the conceptual ideas I was trying to get across was that the electrons inside here would create the magnetic field. And so all magnetic fields were created from the movement of charges. And calculating the magnetic field from those moving charges is going to happen next chapter. And I want to emphasize that. We are just going to say then that a magnetic field is created from those moving charges inside. And that's good enough for this chapter. Now, calculating it, as I said, is coming up, but that's next chapter. And it's important to keep that straight, because what we are going to do a lot of is right here. What if we put, say, an electron there? And the electron was, say, moving with some velocity. What we finished on last week, on Thursday, was there would be a force on that electron. And that force could be calculated with this equation. And so the force depends upon four factors. Did you see those four factors? Number one, what is the value of the charge of that charged particle moving in a magnetic field, and also the angle. And so the magnitude of the force depends on not only how much charge and how much is the magnetic field, but how fast is it moving and in what direction, what angle. And it's those four factors that we're going to study for the rest of this chapter. If I could kind of summarize this one doesn't work quite as well as the other chapters, but since I like to say it and you guys used to think it was funny, do you want to know all the answers to all the homework problems in this chapter? This is it. This is the fundamental idea that there is a force on a charged particle moving in a magnetic field. This is how you calculate the magnitude of the force, and the direction, of course, we got by the right-hand rule. And everything we do today is going to be applications of forces on charges moving in a magnetic field. And so that's what I want you to see, starting with wires and current. And so that's why I put this picture up here. Yeah.
So you can go the other way. You'll find what to produce a electric charge.
I didn't quite follow. You can go the other way, yes. And you can produce electricity. Oh, yes, and we will do that. Now that's a couple chapters away, so I'll hold off on that. But yes, reverse works just as well. And what I showed you, and I want to show you again, was this setup, where I had a magnet, a very large magnet, I had a power supply, and it didn't work last time. And it's, there we go. This time it's working. All right, thought I was going to double check it. But remember last time I had to switch over to this power supply. Let's run through this again. For those of you who are close enough to see this power supply, here is the plus side on the power supply. It runs from this wire to this little tap switch. And so when I touch it, the current flows through this wire, and most importantly, it flows through this metal wire right here. And so the current is going this way, meaning electrons are going that way. So let's stay focused on those electrons. So the electrons would be coming towards me. The magnetic field would be between these two poles. It's labeled north here in red and in green south. And so as we learned last week, good review, is we draw the direction of the magnetic field from the north to the south pole. And so as I take out my right hand and I say, okay, let me put my fingers in the direction of the velocity. And so there's V for velocity. That is coming towards the board. So I grab my right hand and I put my fingers towards the board. Then I cross my fingers, that is, I close my hand towards the magnetic field. And so that's the second in the cross product. So in this case, the magnetic field is going that direction. So that means I'd put my fingers this way, and I guess I'd have to kind of rotate my hand that way so that I can close it towards the magnetic field. So V is into the board, B is over here towards the computer, and so the cross product, and I want to emphasize that, the cross product is down. That doesn't mean the force is down. The cross product is down. So V cross B is down. Now I need to multiply it by the charge. Now these are electrons, so they have a negative charge. So when you take down and you multiply by a negative, you mean the negative of down is up. And so the forces on these electrons should be up, and sure enough, it pushes it up. Yeah.
So instead of moving the electron, would it be possible to move the magnet into the electron field anyway?
Would it be possible to move the magnet?
Yeah, move the magnet instead of moving the electron, making the electron move towards the magnetic field. Why don't you move the magnet itself to move the electron? Because from the electron's perspective, the magnet, because from the magnet's perspective, the electron is moving.
Okay, fair enough, and we will. But I think this is a first learning step. It's easier than what you're saying. So we're coming to that, but not this chapter.
Can you explain how you get the direction of the force?
Okay, cross product. Maybe I should remember. You remember the cross product.
I understand. I guess the right hand rule. I'm getting confused as to why it was opposite.
Right hand rule. You take two vectors, right? The first one listed is the direction your fingers go. The second one, B, is the direction you're going to close your hand towards. So in this case, the first one listed is V, going into the board. So the first thing I do is take my right hand and point it towards the board. And that gives me the option to rotate my hand any direction I want. Okay. In this case, I want to close my fingers towards the magnetic field, which is that way. Okay. And so I would rotate it that way. And then my thumb gives me the direction of the cross product. So this is down. Are you good with that?
Oh, and then there's a negative.
Then I multiply by this number, which is going to have a negative in it. So when it's all said and done, I'll have the negative of down. That means up. And that's how I get up. The opposite of down is up. All right, and so sure enough, it went up. Okay? And so, although taking me a little longer than I had hoped, this is the fundamental equation. This is where we left. Now, as I said, let's spend the balance of today looking at applications of that. And some that you have seen, and maybe others that you have never seen here. But I will start with this idea. Let's look a little bit closer at this wire. Because I'm sure some of you are saying, well, wait a minute, this is the force really on one electron. Is there just one electron here? No. When you tap this, There are billions upon billions. In fact, I think there's more than 1 amp here. Oh yeah, see, this thing goes off the scale at 20 amps. But if it was just 1 amp, as we learned, that was 6.2 billion billionth electrons. So we're 20 times 6.2 billion electrons. There's a lot of electrons flowing here. But my point is this, that if the electrons are flowing, let's say this direction, which in my real one, it's into the board here. So if we call that into the board here, so I kind of twist it, that's in my diagram here, then the magnetic field, which is going towards the board there, if I take that wire and twist it up here, the magnetic field in this picture would be out towards you. And so as a quick review, how do we represent a vector that is coming out towards you? Yeah, and so I'll put a circle with a dot, circle with a dot, circle with a dot, circle with a dot. And this then would be the magnetic field. And if it helps to remember it, this is what an arrowhead might look like if somebody shot it at you. And like I said before, hopefully you've never seen an arrow coming right at you, but I can imagine that's what it might look like, and that's the symbol. Yeah.
Is there also magnetic field inside the wire?
Yeah, and I guess I should have drawn that to make it clear that the magnetic field is actually in the wire. If it wasn't in the wire, well, then we wouldn't have a force on the electrons. Yeah. And I started to draw it above and below, and that could be misleading. It's actually in the wire, yeah. So the magnetic field then would be coming out of the board if I kind of take what I have there and twist it 90 degrees. So the magnetic field is coming out towards you in this picture. The electrons are going towards the computer. Again, if I did the right-hand rule, I would take this and go put my fingers in the direction of the velocity, rotate my hand so I can close it towards the magnetic field, and the cross product would be down. And I want to emphasize, the cross product is down, because now to finish the equation I got to multiply by the charge in front, and these are negative charges, so I would get a negative of down or up, and so the force would be up.
I thought you said in the beginning that you're going to have moving positive charges like electrons.
No. I apologize if I said we're never going to have positive ones. We never have the positive ones moving in something as simple as a copper wire, because then the electrons are moving. But we could just as easily take one of these copper atoms by itself, strip a bunch of electrons, maybe all of the electrons, and just have the nucleus, and then shoot the nucleus by a magnet. And then we would have a positive charge moving by a magnet. Yeah, so there are going to be many examples where we can have positive charges. Yeah. Okay, now the first extended, what I'll call the extended application, as I said, everything's going to come back down to this one equation, but the first extended application of this is to say, well, wait a minute, this is the force only on one electron. Don't we have many electrons? And so if you say that the force, which is QV cross B for 1, then the total force would be the sum of all of those. Fair enough? Fortunately, this is a pretty easy calculation to do. Let me just say they're all roughly equivalent. I mean, all the electrons are going roughly the same speed on average. They all have the same charge. They're all in the same magnetic field, roughly. I mean, I know this is probably not a perfectly uniform magnetic field. But in the simplest case, let's just say everything about every electron is the same. They're in the same magnetic field. They're going with the same velocity. They've got the same direction. They've got the same charge. And so this just simply becomes N times V cross B, where N is nothing more than the number of, and in this case they're electrons. Could I call them charges just in case they weren't electrons? And so I'm going to just say that would be the number of charges. So again, I wouldn't say this is a big step up. This is nothing more than this equation applied n times for however many electrons I have. But here's why I put that. I want to remind you back in chapter 27. Way back in 27, what did we say current was?
It's actually just the flow of
Yeah, dq dt, it's the flow of charge. And we wrote it this way. We wrote it as the little n, the concentration of them, the charge of them, the velocity of them, and the cross-sectional area of that wire. Do you remember all that? And that's looking a lot like this. So we could probably rewrite this equation based on how much current there is instead of how many electrons do we have. And that's exactly what we're going to do. Let me do this. Let me take the current and multiply it by the length of the wire. And so if this wire had a length L, then, of course, I would get that factor with that factor. And that's the interesting part. What's this factor? That's the volume. And what was little n again? The concentration, the number concentration. So when you put all three of these together, what are you going to get? The number of electrons there. Right? This is the volume. This is the number per volume. So if you take number per volume times volume, you're going to get the number. Exactly. And I'm going to use that right here. And so I don't want to lose my overhead there, so maybe I'll scoot over here and kind of erase this drawing. But our first, as I said, extension of this equation that I'm now erasing is right here, where I can replace those three right here with the current times L. And so the force on that wire would be the current times L cross B. And maybe I need to make that a vector, which is something else we need to talk about here before we go too far. But now I have something that I would say is a little more workable, if you will. And when we go to figure out then how much force is on this wire, I can calculate it based upon how much current, the length of the wire, and the strength of the field. And then the current can lead me back to Ohm's law, and I say, okay, here I have a power supply that is set at 14 volts. Divided by the resistance would give me the current. And my point is, we can get the force total on all these moving charges by not looking at them individually anymore, but collectively, and say, how much current do you have? And this vector is kind of interesting. We need to trace it back to here. For it to work, doesn't that vector need to be in the same direction as the velocity? Right? Or charge times velocity, isn't it? And so that's a little subtlety here, because which way are the electrons actually moving here? Okay, as I stand here and as you stand here, they're moving to the right. But when you put these two together, what direction are the two of those together? To the left. They're the direction of the current. So this might be better listed as the cross product between the direction of the current and the magnetic field. I mean, let's see how it applies here. So let's stop looking at the direction of the electrons for a moment, and now let's look at the direction of the current. So here's my power supply, here's the plus, it comes in here, and the current is going towards you. The magnetic field is this way. I cross B up. End of story. We don't have to now multiply by a negative charge. So in this case, when we're dealing with current, I would say it's probably better not to focus on the individual particles and the velocity of those individual particles, but just go back and look at the direction of the current. And so we can just go I cross B, we get up, we tap the switch, and it goes up. If we reverse the magnet, we would still have current going that way, but now we have a magnetic field going that way. So I cross B now becomes down, and we get a force that's down. And so again, we just have to look at the direction of the current and the direction of the magnetic field. And quite frankly, I like the equation in this form conceptually, but it's not very helpful mathematically. So your author does one more thing. He says, let's not write it this way. Although this is really what we mean, and that's why I stopped there to talk about it. He says, let's write it this way. Let's write it as current L vector. What? What do you mean L vector? Like L has a direction? Well, not really unless we define it. And what the author is trying to say here is if you took a power supply and the wire did something like this, then at some little point right there, that's the direction of the current. The direction of the wire. And like I said, conceptually, I like this. Conceptually, I like the vector over the current because that's really what is flowing. Okay. But mathematically, we can then just do a line integral on the direction of the wire itself. And so it does become mathematically convenient. And so I want to emphasize that. I like this physically. I like this mathematically. And this is what you'll see the author write. If you go to calculate this force, you just want to say how much current is there. Because one thing we remember from our circuits is that this whole wire is going to have the same current in it. So we can just have a number associated with current and leave it alone and not worry about direction. The direction then would be defined as the direction of the wire. And since our wires tend to twist and turn, you might say that this really is only valid in a very microscopic distance. Because if you have a wire that turns or twists, then the amount of force, which depends on the cross product, right? And the cross product then depends upon the angle. And of course, we could also be at a different magnetic field, so the magnetic field might have one strength here and a different strength over here. And so, since we are, again, more sophisticated and know calculus, we can say that a little bit of force, meaning a little bit of force right here, would be calculated based upon those four factors: how much current, what direction is the current, what is the strength of the magnetic field, and what is the angle between the wire and the magnetic field. And so there's our four factors. And so I'll put a box around it, but maybe I should put a box around the extension of this. If you then add up the force all the way along your wire, that would be the total force. And we would need to then do what we would call a line integral. We would need to add up the infinitesimal forces everywhere along this wire to figure out what is the total force. It's why I called this picture up first. I thought this would be a good place to start. Let's take a look at this. And so A is showing you a wire that is in a vertical position with a magnet, North Pole to South Pole. And then B and C and D are extensions of that. And so kind of looking at this, if you take this magnet, this three-dimensional picture is trying to say what we have is we have a magnetic field going into the screen. So you can see in green magnetic field with X's, which I did dots. What do the dots mean again? Magnetic field coming out. What do the X's mean? Magnetic field going in. So in their drawing, they are showing the magnetic field going in. And if you wanted to know how much force is on that wire, you would need to do this integral. Now in this case, most of the wire is outside of the magnetic field. Most of it is where the magnetic field is 0. So outside of the magnetic field, over here, how much force would be on that part of the wire? 0. And so as we added up the force on this wire, we would say 0, 0, 0, 0, 0, 0, 0. The only chance, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The only chance of getting a non-zero force is when we enter an area where there is a magnetic field that is not 0. All right, so that is only inside of the poles of this magnet. So then, as we get in this area, you'll notice in picture B here, they said the current is 0. So even though there's a magnetic field, how much force is there? It's 0, right? I mean, if you put a 0 there, it doesn't matter how big the magnetic field is, you're not going to get a force. So you only get a force when you have current and a magnetic field. And in this case, we got to watch the angle too, but they've set it up at 90 degrees. And that's what picture C is. C is saying, well, take a look then on this part of the wire that's actually in the magnetic field. They've got a current going up. And so if you take your right hand, and if you put your fingers in the direction of the current, and you close your hand in the direction of the field, you will get over to your left. And so sure enough, they're kind of showing this wire bend over to the left. If I reverse the direction of the current, then when I go to do a cross product, I would take my right hand and I would start with my fingers going down. And then I would need to adjust until my palm is pointing inward so I can close my fingers inward, and my thumb now is pointing to your right. And so sure enough, the wire bends out. And so that's what I meant by this is our first application of this equation, the force on a wire. Yeah.
So if we go back to our original force cross product, our QV cross V.
Yeah.
If we apply it to part C and D, then are we assuming that the charges are positive moving along the wire?
You could, but you don't have to. And so let's not. I mean, they're not really positive charges that are moving. If this is a wire made out of copper, it's really electrons. So if we go back to the fundamentals, we should get the same thing. I'll try it. So in this case, the current is indicated this way. That means the electrons are going that way, right? So the electrons are going down. So if I were to put my fingers in the direction of the electrons and close my fingers towards the magnetic field, I would get over, well, that's your right, my left. It gets confusing. All right, so, but this direction, right? That's the cross product. Then I'd have to multiply by the charges that are moving, which are electrons. So then I multiply by a negative number, which makes them that way. And so sure enough, they get the same. And the same here. So again, go back to the fundamentals. That works fine. Or work it out and come to the force here. Right? And in fact, maybe it's worth seeing again, but you saw this one. If I kind of remove this one here, and I take that magnet and I just take a wire, and I put it in the magnet. That's kind of what this picture is showing. Right now, I have a wire where the positive is here in the red, and the current would then be going this way. The magnetic field is that way. And so if I go current that way, and close my hand towards the field, I should get up. And so on this section of the wire only, because that's where the magnetic field is, there should be an upward force. This section of the wire, you might say there's no force. And of course, right now, without me turning on the switch, there would be no force because there's no current. But if I touch this switch, I should produce a force, and in this case, an upward force, right? And so there's the force on the wire. Yeah.
Does the magnetic field only between those two ends, or does it cover the whole magnet?
Most of the magnetic field is in here, between these, and so this is kind of like I erased it, but this is the bar magnet with the poles twisted around, and so from north to south is highly concentrated between them. We call these horseshoe magnets, and they make the field in between very strong, like that picture.
When you lay down the wire, though, it still goes up, but it's out of the scope of the magnet.
Well, fair enough. The strongest field would be right here. Is that what you mean?
Yeah.
but even down inside the opening part, there's still a pretty good field. And so it's enough to lift it up. And then once it lifts it up, it puts it in this area where there's a huge field. And then that just launches it way out. I guess it's up, and then it launches it up, and then the tension kind of pulled it towards me. Yeah. And if I switch the direction, it's kind of boring because now it's down. And so pushing it down, you don't see much of anything. It's already down. I mean, you can see it kind of flex that way. Okay. Yeah.
Could a magnetic field ever be so strong that they actually like combine the north and south, the horseshoe magnet?
Oh, I suppose so. I mean, if this was so powerful, I guess it could bend the metal. I mean, it's pretty thick metal, so it's not gonna. But it could be that strong.
So when they touch each other, do they still have magnetic field?
No, now the magnetic field, yeah, there's still a magnetic field inside, but it's probably overall less, so there is a loss of energy. But that's okay. I mean, not a loss of magnetic energy, if you will.
Where would the north and south be? The north and south is touching?
At that point, I don't know if I'd call it a pole, a north pole and a south pole, because it loops all the way around in a big circle now. And so like a circle, where do you start, where do you end? Yeah, so you don't have a good place to say. In fact, the magnetic field really is already doing that. It goes from north to south, then it goes through the magnet and back around. So it's really already in a circle. The only reason we label a north pole and a south pole is because there's a gap in the circle where I can put things in. I can't put something inside the metal piece. But they're really, from a physics point of view, there's no difference between when they are completely closed up and the way they are now. We still have a magnetic field that loops around in a full circle. It's just I can't put a compass between them once the solid metal is there. Yeah. All right. So let's keep going with this, because I think maybe one of the most interesting applications is shown next. Watch this for a moment here. What if I were to remove this big magnet? I'll just set it off to the side here. And then just take this wire, and I'll even remove this little compass so there's no magnet. And I'll move the rest of this one over here a little bit. And I tap the switch now. Does the wire jump, move, twist? Why not? Is there no magnetic field?
Just by the wire itself. But
now your author takes a little more time in chapter 30 to talk about this. But I think it's worth mentioning it now. Is there a magnetic field on this desk? Yes, there is. The Earth makes a magnetic field. So let's take a moment here and talk about, well, what's going on with the Earth? I mean, the way we began this whole chapter was to simply take a compass, set it on the corner of this desk, and say, what's our definition of a north-seeking pole on a compass? Well, the side that points north. And so what I want you to mentally have in store is that if this is the Earth right here, you can think of inside of the Earth as a magnet. Now, I'm not trying to say that centuries ago some aliens came and dug a big hole and put a bar magnet there and buried it and left, okay? But what I am trying to say is all magnetism comes from moving charges. And without getting too much into Earth science here, we do know that the center of the Earth is a molten core. And we also know the Earth is spinning. When you put those two things together, the fact that you have hot liquids that then the thermals rise, then the Earth spins, these rising currents in the fluid, in the iron core, then subject to the rotating the Earth makes a spin, and the combination of all of that, in a very complex way, makes a magnetic field. And so again, in no way I'm trying to say, do I have a bar magnet buried in there? What I am trying to say is I have roughly the equivalent of a bar magnet buried in the earth. And so one of you brought it up earlier then, that if you have the earth right here, and you take Santa Barbara right here, and you take a compass, if you hold that compass level at Santa Barbara, and so in this picture, maybe I will put Santa Barbara maybe right about here, a latitude of about 34 degrees north, then the magnetic field comes out near the bottom of the earth, arches around, and goes in near the top of the earth, something like that. So if I am here at Santa Barbara, what would the magnetic field look like just from the earth? See, I moved this one out of the way. I moved these out of the way. I ask again, is there a magnetic field right here? Yes. Now, it's not much, granted, but there is a magnetic field. So I thought I would take this as an opportunity to say there is a magnetic field. And what it looks like is something that is kind of pointing into the earth. It's kind of pointing towards the north as it points down. The pointing north you probably already expected. This is where we got started. But what you may not be as familiar with is what we call a dipping compass. Remember, a compass will point in the direction of the field. And when I hold it this way, that compass really wants to dip down. It wants to point in the direction of the field. But it is unable to because of the way it is mechanically mounted. And I think some people come across that by saying, okay, in Santa Barbara, what I have is I have a magnetic field that's horizontal. That is not the direction of the magnetic field in Santa Barbara, or any place else other than a few spots in the world. Most of those magnetic fields anywhere on the world is either pointing down into the earth or up out of the earth. And so if I tilt it like this, and you have, again, what I call a dipping compass, this will indicate, I think, a better picture of what does the Earth's magnetic field look like. And so as we stand right here, imagining ourselves right about here, actually maybe here would be a better indication because you can see it's tilted, but maybe Santa Barbara's right about there, then I should have a magnetic field. And so when I stand here, and more importantly, when you do lab, and we get into lab, and I say, okay, you want to measure a magnetic field, but don't forget about the Earth's magnetic field. You need to know its direction. And so is the Earth's magnetic field that way? No. Is it even that way? No. It is that way. It is towards the north and into the ground. And again, that's what this little dipping compass seems to indicate. Yeah.
This might be more of an earth science question, but why is the South Pole on the North?
So there's a couple things I want to point out here. Notice then that this equivalent magnet that's buried in here, notice it says south in the geographic North Pole. And somebody else brought this up. That is a consequence of the way we defined a north-seeking pole. I'll come back to here. Why did we call this end the North Pole? Because it was attracted towards the geographic north, right? But we also know that opposite poles attract. So, if you're going to call this side a North Pole, the one, what I'll call it, you hold in your hand, then it's going to be attracted to the opposite pole that's buried in the earth. So that means buried in the earth, a south magnetic pole must be in the geographical North Pole. Opposite poles attract. So it's a consequence of our naming strategy. And our naming strategy was, what do we call a north-seeking pole? We call the one we hold in our hand the north-seeking. Therefore, the one buried in the earth, we must call a south pole. I don't know if that's such a good idea of the naming, but that's what we have and that's what we live with. Oh, bunch more questions, yeah.
What does it mean when things reverse polarity?
And when I say in the geographic North Pole there is a magnetic South Pole, what I mean is right now that's the way it is.
So what happens with things?
So getting away from the magnet here for a moment, if you were just to watch water flowing in a creek, you may stand it and watch the water hit a rock, and it may flow around the rock, and you would see kind of a little turbulence, a little whirlpool you might call it. And if you watch carefully, it'll go this way, and then some water will come in, and it'll start going the other way. And so it will go one way for a while, and it'll go another way for a while. Now, that's exactly the turbulence that's happening in the center of the Earth. These charges will flow one way for a couple thousand years, 100,000 years, then it'll flow the other way. When it flows the other way, then we are going to have a magnetic field the other way.
Does that have any effect on our technology?
I don't think it'll have enough on our technology. It has some other interesting, possibly significant consequences that we'll see here in a few minutes. But this magnetic field shields us from outside radiation. And during the flipping process, the Earth is probably not shielded. And that's a big question that evolution biologists struggle with. Does most of the evolution happen during the flip of the poles is a really important question. Because at those points, there's probably the Earth is getting bombarded with massive amounts of extraterrestrial radiation. And so things may die and things may evolve, and the things that survive are different than the things that were before the flip, is kind of the question. And I'm not sure how far along they've answered that, but the fact that it's flipped is very evident from the mid-Atlantic rift and the magnetic fields we pick up in the mid-Atlantic. Yeah.
So when we want a compass reading, how come you hold the compass flat if the magnetic field's actually pointing down?
Well, because you just want to know which way is north, right? But you say you do, but not everybody does. Somebody who's really an expert in compass readings will first hold it flat to get a reading of which way is magnetic north. Then they will rotate it 90 degrees and see how much it dips. Because as you can see here, there's some very valuable information in how much it dips. The further north you go, the more it dips. And so I could tell you what my latitude is by knowing how much that dips. And so if I know that I'm flying a plane or navigating a ship or a submarine, and I know that I want to get as far north as Portland before I head in, I can look at the dip on my compass, and I'll just keep heading north until I get to the appropriate latitude, and then I will head into port. Humans kind of forget about this, but how do these crazy homing pigeons find their way home? It's these magnetic fields. And I don't think scientists completely know exactly how it works, but they know that when they've taken pigeons' brains and dissect them, they are loaded with iron and magnetic materials. So unlike human sensories, they have a lot of magnetic. In fact, you remind me of a great story. I got to tell it here. Because I was a graduate student. I was at UCLA. And we were right next to the medical center. So we had our physics lab, and actually it was engineering lab here. And we worked a lot with the medical department, and the medical department worked a lot with the biology department. And so there was a lot of overlap. But I got to know this guy who was working on his PhD in biology, and what he was interested in is the migrating patterns of lobsters, which that alone struck me as odd. I didn't know lobsters migrated, but they do. I'm from the California coast, and I guess they don't migrate on the California coast. I even get confused when I see the ones with pinchers, and I go, that's a lobster? Oh, yeah, that must be an East Coast lobster, right? Okay, they do have pinchers. But in California, we don't have those pinchers. But apparently in the Caribbean, lobsters do migrate. And they, according to him, they do that because of the hurricane season. And so they're in shallow water until hurricane season comes, and then they have a long migration, and they have to go across these open sandbars and get to deeper water during hurricane season, otherwise they won't survive hurricane season. So they actually migrate. But they go a long distance, and the question was, how do they know where to go? And they were testing to see if it was magnetic. And so it was neat. They took this giant tank, it's about the size of this room. They caught some Caribbean lobsters, they brought them back, they put them in the tank, and under the tank they put a giant bar magnet. And the lobster was just kind of strolling along the bottom of the tank, and then they just took the magnet and they reversed it. And it was kind of neat to watch this lobster. The lobster just kind of stopped. Whoa! And it just sat there for about 15 minutes, and then eventually turned 180 degrees and started walking to the other side of the tank. And they just kept doing this every time the lobster got to one end of the tank, and it was just overwhelming evidence that it was clearly following the magnetic fields in this bar magnet in this tank. So other animals do navigate. I think the theory is that sea turtles do the same thing, but nobody really knows how they do it, if it's by the moon and the seasons or if it's magnetic. Butterflies, the monarch butterfly, another crazy one that I don't think anybody quite knows. I don't know the answer to how they know their patterns, especially the monarch butterfly. I mean, they migrate back to places that they weren't even born. And in fact, their parents weren't even born. So they go back to where their grandparents were born, who died before they were born. Weird. But somehow they know how to get back to where they're supposed to go. So that's a really weird one. Huh?
Wait. So you said earlier that the dip of the compass is very unique to every single spot. It's very unique to very few spots.
Well, latitude, yeah.
Latitude.
Right.
So it would be possible to navigate longitudinally if you could measure how subtle the needle dips.
Yes, and that's what penguins do. Pigeons do.
Longitude, not latitude.
Oh, no, because it's not unique. You can get no, because anywhere along the magnetic equator would be the same, for example. Yeah. And so you'd have some issues there. Another thing to point out is notice that the magnet that's in the Earth is not directly in line with the rotation of the Earth. And the reason I brought this globe out was to kind of show you that. Yeah.
The magnetic equator, is it going into or out to?
Well, then at the magnetic equator, if I were to take a dipping compass at the magnetic equator, it would be level. Because the magnetic field would be coming out below, then it would be horizontal, and then be going in. Yeah. So I know when I'm at the magnetic equator when my dipping compass is horizontal. So I brought,
Where is true north compared to magnetic north?
I'm glad you asked that. Hang on for just a second then, and I'm going to put a map here on the board here. But the globe, this one, if I kind of tilt it to your position, it actually shows right there, this is the magnetic north, which is really a magnetic south pole in the geographical North Pole, which isn't really at the North Pole. Did you follow that? Oh, good. Okay, and so there's where your compass, whoever asked that, would be pointing. It would point kind of towards this direction. So as we are in California and we hold a compass, it will be off a little bit from true north. And so what we call magnetic north and geographical north are slightly different. And your cell phones and your GPS usually have a compass in them that says, okay, point north. And then you have a little option. Do you want it to point magnetic north or geographic north?
It just means we made our maps poorly. It's arbitrary where the North Pole is.
You mean the geographic north?
Yeah.
No, this is I think I consider the geographical north far more significant than the magnetic
I
north.
think it's arbitrary. I mean, if you think like the galaxy, you can just, there's no orientation to it, so like,
No, but
how do you put an orientation to yours?
well, if you mean we could have just as easily called this north, fine.
Yeah, exactly.
Fine, but there is something unique about the axis of rotation.
But not
Okay.
north and south,
Right.
really.
Right. So you could call it by any other name, certainly.
Yeah.
But there is something unique about that axis, and that's what the Earth spins around. Yeah.
The orbit around the sun, it's not tilted, right?
Well, okay, fair enough. And that's why when you do a globe here, and maybe I should emphasize then I've got two tilts going on. If you think of this as the sun, then the spinning of the Earth, maybe I'll do it this way so you guys can see, the spinning of the Earth is tilted from the plane of the orbit. And that's about 23.5 degrees. In addition to that, the magnetic north is tilted, as shown here, about 11 degrees off of the rotation. So there's really two tilts. There's the tilt, but has to do with the orbital plane and the rotational axis. But there's also the tilt, which I'm trying to emphasize, is the tilt of the magnetic field. And so you pointed out, our compass would not point truly north. And in fact, in our case, our compass would point a little more towards the east. But in other parts of our country and other parts of the world, it may point towards the west of north, depending on where your compass is. Yeah.
Does it deviate that 11 degrees because of the spinning of the
No. I mean, again, it's this turbulence that is going on inside of the Earth. And so that's the turbulence we have right now. And that turbulence is changing. And we have more than enough evidence to show that it may be 11 degrees now, but it was, I think, 11.2 a century ago. And there's slight changes. I am not sure the exact numbers, but we have measured enough changes. And there's a lot of thought that maybe we are at that point now in our Earth's history where the direction of the flip is coming up, you know. And because we've measured it changes in the last 100 years. Yeah. This, I think, answers your question a little better, whoever was asking it, is that what direction would a magnetic compass point? And so you can kind of see that along at least the California-Mexican border, we're a little bit further than that. Where's Pacific Palisades, Malibu, is that Point Conception? All right, so we're probably right about there. But right about there, we're somewhere between 15 and 20 degrees off if you were to hold a compass. And if you were to follow it, you would be not going true north. And in short distances, that's probably okay. But long distances, if you're out backpacking or flying a plane or navigating a boat, you have a map that shows you which way is true north and which way is magnetic north. It's also highly influenced by what the rocks are made out of. So you can see as it meanders through the very rocky areas of Southern California, what direction it actually points can change significantly. Whereas you go through the Great Plains, it's like, yeah, big deal, you know. There's nothing magnetic to affect it here. And so, and of course, look through the Northwest. I mean, you know, there's the big changes because of the local effects, because of what is the mountain is made out of. Is it magnetic material or not? And so that's this whole thing. In fact, speaking of stories, it reminds me of a story that way back in the Cold War time, crazy pilot flies his plane wanting to go over the North Pole. All right, so you leave somewhere in the United States and you go over the North Pole. Now, if you're flying over the North Pole, so I'll just kind of hold it this way so you can see. So I'm flying over the North Pole. Which way would your compass point? Wouldn't it be pointing towards the United States and Canada? Well, this pilot looked at his compass and said, okay, I want to go back south to the United States. So I better go opposite of the direction of the compass. So he turns opposite of the compass, which takes him which way? Over Russia. And he ends up over Russian airspace with a bunch of, what do they fly? MiG something, and forced him to land, accused of being a CIA spy, and imprisoned for about 3 months before they finally were convinced that it wasn't a CIA agent, it was just a stupid pilot. Stupid American, you know, and sent him back. And so, okay, now all of that was a long discussion to give you an idea of the Earth's magnetic field. You're going to need it. A little bit this chapter, a lot next chapter, and a couple of labs. We really have to have a good mental picture of the Earth's magnetic field. And I think those two pictures show it quite well, because I ask again, is this wire in a magnetic field? Yeah, and it is a very weak one here. But I have a lot of current. But nonetheless, I don't see the wire jump or move. It might be strong enough. I'm not sure. I want you to see something even more important here. And that is, what if I have a wire that is completely in a magnetic field of the same value? In other words, what I had been showing you up to this point, where just a section of the wire was in a magnetic field, what if this whole wire was in a magnetic field? What would this equation give me? Yeah, and hopefully you can see it, that maybe the first thing I would do is to factor out the current. That's the nice way of writing it mathematically like this as opposed to like this, because then I don't have to worry about the direction. I can just take current as a constant value as long as I don't have any nodes, and then pull it out and say, all right, it's the same current everywhere. And what I'm trying to illustrate here first is that I could also then take the magnetic field out, right? Because the magnetic field has the same value. Yeah.
And you could only do that if the whole thing is in the magnetic.
Right, right. And so I'm saying the whole thing is in the magnetic field. And here's another interesting consequence. What does this give me? Now I'm adding up vectors. I'm not just adding up length. So if I go 3 steps to the right, then I subtract 3 steps from the left, what's my total integral?
0.
0. And so by the time I do a complete integral, all the way around, I'm going to get 0. So kind of boring. I touch this in a uniform magnetic field, nothing happens. And of course you said, well, maybe nothing happens because the field's not strong enough. Maybe, probably, but also what I want you to see is there is no net force. But that does delete something far more interesting. Let me go back to chapter 29's picture. And your author shows this in figure 29 really well. No, figure 20, sorry. Right here. And he says, let's take a close look at a rectangular wire. Let's just put a uniform magnetic field. Let's go through our right-hand rule here. Let's look at wire number 1 up there at the top. Okay. How much force is on wire number 1? 0. Why? The angle is 0. Or you may say the angle is 180 degrees to be more specific. But so remember, when we go to take a cross product, there's an important piece here, which is the sign of the angle between the current and the magnetic field. So in the wire number 1, the current is going this way and the magnetic field is going that way. So you could say that's sine of 180 degrees. And so how much force is on wire number 1? 0. What about wire number 2? Does it have a force? Yeah, in what direction? Good. So if I were to take wire number 2, I'd put my fingers down, there's the current, I would close it towards the magnetic field, and my thumb would then be pointing out of the screen towards you. And so yes, there's a force on number 2, it is towards you. Keep that in mind. Let's go to number 3. How much force is on number 3? Okay, 0 again, all right. How about number 4? Yeah, I put my fingers in the direction of the current towards the magnetic field, and I get into the board. And so, on wire 2, it's out of the board. On wire 4, it's into the board. Now, how do those two forces compare? Yeah, they're equal. And maybe you can see it here in the math that you would have the same current, you would have the same length, you would have the same angle, and you're in the same magnetic field. So your net force is 0, as to be expected. Isn't that what we said? But more interesting here is not that the net force is 0. What about the net torque?
It is not 0.
Yeah, this will spin. And so again, going back to Physics 121, in fact, I would probably guess what gives students probably the hardest challenge of this chapter is not the magnetism, but they've forgotten how to do their 121. And they've forgotten about moments of inertia, and they've forgotten about torque. So we need to go through a bunch of examples that involve that, but this should spin. And the picture down here is projected like that, where what we would have is, here's wire number 2, so they've kind of taken this and moved it out to here and say this is up and this is down. This wire would not translate. The net force is 0, but it does have a torque. And viewed in this picture here, there would be a torque from this one making it rotate in a clockwise direction, and there would be a torque from this one making it rotate in a clockwise direction. And so when you add up 2 clockwise, you get clockwise. This is going to rotate. And we'll calculate that in just a minute, but why don't we just give it a try first? Here, I have what hopefully looks a lot like that rectangular loop.
There's so many coils though.
Well, this has a lot more. This has 20 of them. But I'm going to wrap it around, and so what happens for one also happens for the other 20. But I'm going to place this on my little holder here, and I'm going to make a magnetic field going from, well, you guys here, from the left to the right. And so unfortunately that will block your view a little bit, but I've got some pretty good size magnets here, and I'll pull them apart for a second. And you'll see that this side says it is a North Pole. Maybe I should just confirm that. This is a North Pole. It should repel that North Pole, right? Oh, and it attracts. So this must really be the North Pole. Ah, liar. Okay, I'm glad I checked. But either way, I'm not going to really worry too much about direction for this little design. But what I am going to do is place the 2 magnets here. And so hopefully what I have is a wire with a magnetic field through this. And if I kind of rotate this on its side here, as you'll see, that will hopefully give it a torque. It'll give it a rotation, if you will. So I'll go ahead here and I'll shut my power off here. But what if I take this power supply and I plug the current in on one side and the current in on the other? And I didn't pay any attention to what direction any of those are, so I'm not going to try to figure out which way it rotates. But it's going to rotate, either clockwise or counterclockwise. There's going to be a net torque. So if I turn this up to full power, let's see. Yay, what happens? And so, it's not the best electric motor in the world, but I hope it sets the stage of this is how an electric motor works. It supplies a torque as it spins around here. And maybe I'll just run through it real quickly here, and with an added feature, here is our model of that electric motor. Okay, what I have is I have a magnetic field. Now, in this case, they're sitting north to south that way, so that's a little bit different. This thing keeps falling off. It stands. Actually, well, you saw it. All right, we'll turn it off altogether. But this model looks like my field direction is kind of opposite of the one your author has. But let's go with it. It's put a big magnet here and another magnet here. These aren't real magnets, by the way. Just pieces of wood painted. But to illustrate it, this is a North Pole, this is a South Pole. So in this case, the magnetic field would be this way. And so what I've done is I have taken my power supply and connected it up. All right. And I will bring this over, and not that it's really going to work, okay, because it's, like I said, it's not really a conductor here. But let me put a positive on this side. That's kind of what's written on here with chalk. And then a negative on this side. But if we look closely at this, the current then is going to come across, I'll turn it this way here, and there are what we call brushings. And the current goes through this brushing and touches what we call the commutator. It goes down through that wire, and that's the part I want you to see. And so as the current goes down that way, and I take my right hand, noting that the magnetic field, I've got current down, and I've got a field that way, and so that's going to put a force on this wire in. This one here, the current would go down and come up. Magnetic field is still going that way. So current's up, rotate my hand, close towards field, force out. And so this one goes in, this one goes out, and that should twist that way. Now if that's all it did, we'd be in trouble because it would twist this way, and then what would happen when it got here?
You go the other way.
And it wouldn't really make a good motor in of itself. So notice the added piece here on the commutator is that you are making electrical contact, making the current go down. As it spins, notice it breaks contact, reestablishes contact here, and the current that was going down and up, when it gets over to here, now goes down. And so when it passes this point, the current essentially changes direction because of the commutator, and now goes down, which then draws it around and around and around. And so it breaks and unbreaks the contact. And I'm sure you saw that with my commutator here, and you'll see little sparks every time you break and unbreak your contact.
That's Tesla's, right? In the inverted motor. Tesla's invention.
Oh, yes. Yes, exactly. And this is the simplest motor and the first thought about electric motor, and so that's why we start there. This is one that I can easily build for you, and you can see it. Don likes to call it the Flintstone motor. And so I told him this morning, hey, get that Flintstones motor out. The students would like to see that one. Yeah.
Another motor is made with constant reversing of the polarity of magnets, right? Is that
Yes. And of course, we could have done the same thing with reversing the polarity of these magnets. And we will learn more about that soon, but we're not one step at a time there with our magnet. Let's do a quick calculation here then. And as I said, all I'm going to do for the balance of this chapter is keep applying that force. So let's come over to here. Let's say, could you calculate the net torque here? All right. So I'm going to take us back to Physics 121. How do you calculate torque? Okay, so R crossed F, right? Now, we need to talk about all of these as a nice review, but where are we getting the F from? Okay.
But the problem is the magnetic torque changes as it angles down. That's the big spin.
Exactly. So this is going to be a fun calculation. Yeah. All right. So why don't we do this for a moment? Why don't we do the easy case? What if it was a straight wire in a uniform magnetic field? That's kind of what I have, right? I mean, I've given kind of the easiest case I can here. I have a straight wire, wire number 2, in a magnetic field, right? So if I were to calculate this, I might say it would be R cross the force on number 2 plus R cross the force on number 4, right? Those are the two that we said had forces on them. Wire number 2 and wire number 4. Okay? So, let's keep going. R cross. How would you get the force on wire number 2? Yeah, exactly. We'll come back over to here. And what was nice about this is that the current in wire number 2 would be the same value. So I'll just pull it out. That's I, right? And then we would have an integral of ds. And the angle wouldn't change, so wouldn't that just, integral of ds just be the length of the wire? And so the length of wire number 2 would be a distance a, right? Okay, so I'm going to write this as I A cross B. R cross, and how do I get the force on number 4? Yeah, and maybe I need to be more careful with my notation. What do I mean here by A? I guess I really mean wire number 2, don't I? I mean, it has a length of A, but it's pointing down. And I want to emphasize that because over here, on wire number 4, it has a length of A also, but what direction does it point? Up. So I want to keep track that those are different directions. Okay? And so I got a little bit of work to do. In fact, I've got 2 cross products, don't I? All right, so let's not confuse the two. And actually, I should say I have 2 cross products in each of the 2 terms, right? But why don't we start then with this one? Why don't I start with the magnitude of this one? Wouldn't that be I, A, B, sine of? What would the angle be? Well, I guess kind of in this picture it would show 90, right? But what about when it turns a little bit? What if it's sitting here, and then maybe it turns a little bit to here?
45?
It's still 90 if you're looking at the right angle. What about here? Still 90. What about here? Still 90. What angle am I looking at? I am looking at the angle between the wire and the magnetic field, right? And so the magnetic field is always going this way, or this way, okay? And the wire is always going up and down no matter where this wire is. Isn't there 90 degrees between the horizontal field and the vertical wire? Okay, so this comes out to be 90 degrees, which is really nice because that means I just get I, A, and B for its magnitude. Now, you already told me what direction would it be, and maybe we should, go to this picture, but you said out of the board here, so down here it's kind of up. There's force number 2. Okay? Maybe without too much work, is it okay if I do the same logic here? That this 2 would be an I, an A, a B, and sine of? Yeah, 90 degrees there too. And so that kind of reduces to I, A, and B also. All right, so far I've kind of simplified that a little bit. Now, let's do the second cross product. The second cross product comes from the equation for torque, the R cross the F. And so if I put these together, this would be R, the magnitude of R, the magnitude of I, A, and B, and then the sine of what? And I think your author has the next picture with this rotated a little bit. He says, let's look at it in its rotated position. And so if you take what was a moment ago flat and you let it rotate a little bit, Ah, good. And I lost that picture here. But the length of R is b over 2. So I can replace this with a b over 2. But what about that angle? Sine of what angle? Yeah, it's the angle between what? Yeah, we're back to physics 121. Isn't it between R and F? Okay. So, isn't this the angle between R and F? So what's this angle? Isn't that the supplement of that? And so the author's going to play a little game here, if you will. Isn't the sine of an angle and the sine of its supplement the same? And so really, when you're doing your cross product, the real angle you want in a cross product is the angle between R and F. But your author's going to take a couple of quick steps here that are easy to overlook. He says, well, this is the angle between R and F. That's really the angle you want. But since we want the sine of that angle, let's take the sine of its supplement. So he says, well, that angle would be theta. Now, if that angle is theta, and we want the sine of that angle, now remember, we really want the sine of that angle, but the sine of that same angle would be identical. Then he steps over and he says, well, then this angle in here would be the complement of that. And that angle here, and he draws a line perpendicular to the wire, normal, right? There's our A vector. Remember Gauss's law, right? An A vector perpendicular to the surface. And he says this angle is theta. So this angle here and this angle here ought to be the same. What we really want is the sine of that angle. But what I'm trying to say is it comes out to be the same as the sine of the angle in that piece. And so as you pointed out, Danny, this is going to change as it goes around here. And it's the sine of the angle. And how are we measuring the angle? We're measuring the angle from between the magnetic field and the normal vector to the wire. Let me set this up again. Here's where we're starting. When it rotates to here, we are really talking about how much of an angle did it rotate. We're talking about the angle between the magnetic field, which is going this way, and the normal vector, which is now here. So in this spot right here, what would be the angle theta? Maybe I should ask it that way. What's the angle here? 90 degrees. Again, angle is between the magnetic field and the area vector. So magnetic field's going that way. Here's the area vector that way. And so I've sine of 90 degrees. Isn't that the place where you get the most torque? And that's what we said. We're going to get the most torque because right now this one is pushing in and this one is pushing out. How about right here? What's the angle right there? 0. And so how much torque do you get? 0. And hopefully that makes sense because in this position, if the commutator didn't kick in, that wire back in the back would be pushing that way still. And this wire out in the front would be pushing that way. And if you pull one wire back and one wire forward, that's not helping it at all to rotate, right? And so there's no torque. And so this motor has the most torque here, and then it decreases, 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 decreases to 0. Then if you switch the direction of the current, it would increase, 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 and have its maximum here again. Decrease, 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 0. Switch the direction of the current. Increase, 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 maximum. Decrease, 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 decrease. And so how much torque you get does depend on an angle. So interesting enough, as we did 2 cross products, notice that every time we do a cross product, there's a sine of an angle. But the first one was the easy one. The first one was always 90 degrees, no matter where the commutator was when it rotated. But the other one, The other one, which has to do with the mechanics of it, is the angle between R and F, and that one is what we're going to call theta. Okay? And so that would be my magnitude of my torque. And in this case, as we viewed here, that torque would be making it rotate in a clockwise direction. And I'm hoping you see, doesn't the same thing work in the other side? The other side, isn't it the same number? Isn't it the same angles involved? And so I can just say double times 2. And so there's the torque for my motor. And fortunately, the 2's cancel off. And so what I end up with is current times AB times B times the sine of the angle between them. And so that would be the torque for my motor. Now, not quite done here, because we can write this in a much more compact form. Isn't that little a times little b the area? And isn't the angle measured between the normal vector? And so, if you look closely at this picture and that equation, this might be nice to draw as A vector cross B. Because A vector has a magnitude of A times B, the area of the loop, and then the direction is perpendicular to the surface, which is perfect because it fits right in with our idea of a cross product. And so we can get a torque out of this and write it as a cross product again. So, no doubt, you are seeing a lot of cross products today, and hopefully that's bringing back memory. Oh yeah, cross products. I remember how to do this. Because now we have a lot of cross products. We have V cross B, we have L cross B, we have R cross F, and now we are going to have what we'll call a mu cross B, because we will put together the current and the area. They tend to be the two factors here that determine how much torque we get, and we are going to call this then the magnetic moment. And so the magnetic moment is a combination of how much current do you have and how much area do you have. It's those two things together, along with the direction of the magnetic moment, that is going to determine how much torque you have. Yeah?
Does it also follow that the volume cross B is something, stands for something?
Volume cross B?
I mean, yeah, because first we had L cross B and then we had A cross B. Area cross B. What happens if you have no volume cross B?
Okay, I don't see volume up here. You're just saying, what if it was volume cross B?
Yeah.
Well, I don't know if I can do that. I have to have a vector. And volume's not a vector. And I don't think we've given area little vector heads. But I don't think we've ever given volume vector heads, have we?
The first was, he means A L B cross C, I think. Like, isn't that like
The volume.
yeah, the volume
No,
of
it's
the
A
current?
dot B cross C.
Yeah, I mean, yeah, there's a lot of interesting things of cross products.
That's a scalar, it's not a vector.
Yeah, that's what he was talking about.
But that gives you a scalar. Okay, so the one I want to put a little box around is this. That as you get to doing the homework problems, you are going to ask, how much torque do you get on that little wire? Here's the idea. That you're going to get the magnetic moment, you're going to get the direction of the field, you're going to take its cross product. Then I'll put an N here, because as you guys pointed out, this is what I will call the number of loops. Everything I derived up to that point was just for one loop, right? And you probably noticed mine, and you even made a comment that I had many loops, and so I need to do that for every loop, and so it would be N times. And so I have N, the number of loops, and there's I would get the torque. Now, I know this one was a bit more complicated than the last one, but I should emphasize, where did this all come from? Force equals QV cross B, right? And so everything I've done, hopefully so far today, and everything I will do, I'll keep coming back to that and saying, okay, there is the fundamental equation. All right, well, let me shift gears for a moment here. Now that I've done a lot of wires with current, and we looked at the force, and we looked at the torque, and we talked about a little bit about electric motors and how they work, what if I just had something like this? What if I just had a single charge, like an electron? Or maybe a proton? And they're moving. But they're moving where there is a magnetic field. And so let me just say there is a magnetic field directed into the board. Again, let's go back to physics 121. How would you describe the motion of a charged particle moving in a magnetic field? What would happen? And maybe before I even put the picture on here, I should pause, let you think about that. I mean, I'll go back to physics 121. If we had an object and it was moving this way, and you applied a force in the direction it's moving, what would happen? Okay, if you give a force, it always accelerates. Fair enough. But be more specific. What kind of acceleration would it have? Would it go faster or slower?
Faster.
It would go faster, right? And so this type of force in the direction it's moving would make it go faster. What if the force is this way? What would that do? Yeah, of course it would make it accelerate, but what type of an acceleration? Slower, right? What if the force was this way? What did we learn? Change its direction. It would make it turn, right? So you remember all that from physics 121? You might even remember this question. At least I hope I asked it when you were in 121. Where's the accelerator on your car? It's the gas pedal, the brake pedal, and the big round thing in front of you, right? All of those make your car accelerate. There are different types of acceleration. This one makes it go faster, this one makes it go slower, and this one makes it turn. Okay, so now I ask. V cross B multiplied by the charge is the force on a moving charge in a magnetic field. So let's put together what did we learn in physics 121 together with our new magnetic stuff. What would you say about the motion of a charged particle in a magnetic field?
There's work.
There's a force on it, right? It does accelerate, right? So does it go faster? Does it go slower? Does it turn? Right, and remember what a cross product means. What direction is the force compared to these two vectors? Yeah, that force is perpendicular to velocity. What did we say back in 121? If we have a force perpendicular to the motion it's moving, what does it do? It makes it turn. That's all it does. Does it go faster? Does it go slower? So does it gain any kinetic energy? Does it do any work? Does it accelerate? Turns. And it does nothing more than turn. And so, if we have a charged particle moving in a magnetic field, this is what figure number 7 is trying to show, is that, take a close look at this. Here is, and I'll use this positive one here, since that's what's in the diagram, but they show a positive one moving across horizontally in a magnetic field that's into the board. If I take my right hand and go V cross B, I would have V that way, close my fingers towards B, and at this point I'd get a force up. And then that's multiplied by the charge, but this is a positive charge. So that keeps the force up. And so what they're saying is you would get a magnetic force that is up, like here. And what would that do to it? Turn. And when it's right here, what direction is the force? Perpendicular. It's always perpendicular. That's the neat thing about this. So if you missed that when we did this last time, let me emphasize it now. that little basic formula is telling you that a charged particle in a magnetic field is not going to go faster, it's not going to go slower, it's certainly not going to go straight, it turns. And in this case, it goes in a circle. They don't show a negative one on here, but what would the negative do?
Other way around.
Yeah, I would put V cross B, and I'd get up. Multiplied by a negative charge is down. So if there were negatives in here, the negatives would then be going in a circle in the other direction. Yeah.
If you, oh, never mind. I was using my left hand. Never mind.
Oh, yes, yes, yes. Warning, don't use your left hand. Especially during a test. I know the test, I see it all the time. I sit up here and people are stressed and they're so busy writing with their right hand that they're doing the cross product with their left hand. And so don't do that during a test. Well, don't do it now either, but don't, especially during a test. I guess that's why you lefties will have a little advantage. You can actually do the right hand rule while you're writing with your left hand.
So what is that center called?
So I guess the center would be the center of the circle, right? This thing would go in a circle.
Center of the circle.
Center of the circle.
Of the motion.
Of the motion of this charged particle, right? And we could calculate the radius, couldn't we? And how would I do that? How would I find the radius of this circle for these charged particles?
Find a force.
Right, so I would have to go back to Physics 121 and remember that if you applied a force perpendicular, it goes in a circle, and the value of that equation, right, the centripetal acceleration was v squared over r. Multiplied by m, and that's the centripetal force. And so if I set those two equal to each other, I would have QVB sine of the angle between V and B equals to mv squared over r. Now in this case, we have set it up, so what is the angle between V and B? 90 degrees. So this is a special case, and it makes sense, it's our easy case. And so the picture we are looking at, the first thing I can do is put in 90 degrees, because no matter where that object is in that circle, it's 90 degrees. And then a couple things cancel, but I guess it's just one. But then I would get the radius of that circle. And so here would be the equation for an object going in a circle in a uniform magnetic field. Yeah.
If we have like a proton that's not in a magnetic field, but it then enters it, will it just kind of reverse the direction and then kind of make it start going back out?
Oh, yeah. So if you had like this dividing line where here comes the proton, and at that point there's no forces on it because it's not in a magnetic field. Once it hit here, it would make a circle, and there would be some radius, and I guess it would make a half circle, semicircle, and then it would exit on back, and we would reverse its direction. And we're going to do that here in just a second. But the idea here is we can now control charged particles with magnetic fields. That's the lesson here. Yeah.
I think I might be missing something. Isn't like the total force over a uniform magnetic field 0 because it's a closed path?
It's not necessarily.
And I'm not, the total force?
Oh, never mind.
Oh.
Never mind.
Okay.
Yeah, magnetic field is
Now, what if it wasn't quite so easy as this? That is, what if the electron was not moving perpendicular to the magnetic field? How would this be different?
No lips.
Ah, good. What if, again, the magnetic field is, say, into the board, as we have here, and this proton, right here, this positive charge, instead of moving straight across the room here, it's, say, kind of moving in at an angle like this. What would you do? Yeah, couldn't you think of the motion that is coming in as made out of two parts? Part that is going across horizontally and a part that's going in the direction of the field? So the part that's going across, isn't that the same thing we talked about? So what about the part that is coming in? What would happen to that? What if a proton was just coming straight in the direction of the field? What would happen? The force would be 0, right? So if you look closely at this, right here when we did the cross product, we said 90 degrees. It probably would have been better to say how much of the velocity is perpendicular to the field. Right? That's the part that makes it go in a circle. Hang on, you still with me? All right. All right. That's the part that's perpendicular. The part that is going with the field. Let me call that the z direction. Nothing happens with that. And so this picture, as somebody said, is probably better described as this. That the general motion of a charged particle in a magnetic field is a helix. And what would happen is it would wrap around in a circle, and the part of the velocity that is in the direction of the field, which in this picture they are saying the field is in the x direction, it just keeps going down the field. And so we have our circle plus our translational motion together. And so we've got a helix. Yeah.
Why does it go down the x-axis and not just go over to the p?
Again, the initial speed. All right, so if this is the x-axis, this way, if you give it an initial speed like this, so that it has a component in the x-axis, the part of the speed that's in the x-axis continues. There is no effect on the velocity in the x direction. And so the velocities that are perpendicular to the field, the y and z component, are going to make a circle. But the part along the x-axis continues on. Okay? And so we get a little helix. All right. Good, you got it.
Yeah, that's why.
Yes? No? Yes? Oh, good. All right, so a good application of this is what we call magnetic bottles. And so what if we made a magnetic field like this? And so here is a tough technological question. How do we trap or store all these charged particles? Especially if they're going close to the speed of light, they have a lot of energy. And we either want to trap them or use them to collide into other atoms to make colliders or to make nuclear fusion. They're going really, really fast. And so how do we control them? How do we trap them? Yeah, and so we call this a magnetic bottle. It's a real simple idea, is that you make a strong magnetic field that kind of weakens, and then over here you make a strong magnetic field. And so what's going to happen, if you look here at the radius, is what would happen to the radius when you entered into areas that had a small magnetic field? The radius gets bigger. And so these charged particles are going around in a little helix, if you will. In this area, their radius gets very large, and so that's where most of their kinetic energy is now in their circular motion. Or I guess they keep their same translational on down the road. But what we can do is we can tighten that circle up so much that they then essentially reflect off the back side, and they're just kind of trapped inside the bottle there. And so there's our magnetic bottle. Shall we add to this? All right. One more. What if I built something like this? This is called a velocity selector. You'll see why here in just a second. But this is going to take us further than any of the other problems we've gone so far. We need to include an electric field. Watch this for a moment. Forget about this green and brown for just a second. The green and brown are going to be a capacitor. Let me get rid of them for just a second. Because we would essentially have, here's our source, and let's say we have a proton moving in a magnetic field. So here's the green in a magnetic field. As we just got done talking about, you would have a velocity this way. You would close towards the magnetic field. You would get a force then, a magnetic force over to the right. And what would happen is it would have gone in a circle. Fair enough? But what if at the same time you put a capacitor between them, a parallel plate, and you charge this plate negative and that plate positive? What would happen to this proton if there was just an electric field? Wouldn't it be pulled that way? And that's what your author is trying to say here, electrical force. And so as this proton moves through this little area of space, it's got two forces. It's got a magnetic force pushing it to the left. It's got an electrical force pushing it to the right. What if you balance those two? It goes straight. Let's do some math here. What I'm really saying is the total force is both a magnetic and an electric. What we just learned in this chapter is that this is how you calculate the magnetic force. We already learned way back in chapter 23 how to calculate the electrical force, right? This one is, as we pointed out in that picture, to the left. This one is designed so that the velocity and the magnetic field are 90 degrees. So when I go to calculate this, I go a Q, a V, a B, sine of 90 degrees, and the force is in the negative I hat direction in that picture. What direction is the electrical force? It is in the I hat direction. If you balance those two, that is, if you want to look when the velocity, when the net force is equal to 0, here is what somebody pointed out last time is very, very useful. The amount of the magnetic force depends on velocity. Does the electric force depend on velocity? No. But the magnetic force does. So, what would happen to objects here that are going slow? Because they are going slow, you would have very little magnetic force and probably an electrical force that is bigger than the magnetic force. And anything going slow through this area is going to go crashing over to here. What about anything that's going really fast? Just the opposite. Anything that's going really fast is going to have a large magnetic force on it. That large magnetic force would dominate the electric and it would crash that way. So only the ones with the right speed, and hence the name velocity selector. Only the ones with a certain velocity are going to go straight. And so if you make an opening over there, everything that comes out of there is going the same speed. Not too fast, not too slow. It's our Goldilocks selector. Perfect. Not too fast, not too slow. Yeah.
Is that kind of how a cathode ray tube works?
It's the beginning of a cathode ray tube. Yes. This is our first step in a cathode ray tube because we are now deciding what speed each charged particle will have. Anything going too fast or too slow is eliminated and doesn't get on the other side of our selector. Yeah.
So you can put any magnitude of magnetic field and electric field as long as you go in the
Right. So if I follow through on the math, set this force equal to 0, there is a Q on each side. So how much charge they have is not important. If I move this over to here, I get VB equals to E, or equals E over B. And so everything that has a speed that is equal to the ratio of E over B will go through that selector. Anything with too much or too little deflects one way or the other and doesn't make it through. And so, as you said, I can adjust my electric field or my magnetic field so that my velocity selector does just that. It has only a particular speed.
So can you slow down an electron like really, really slow so that you can see it?
It's too small to see. I don't care how slow you go. It's not that we can't see electrons because they go too fast.
Make it really slow based on that.
Oh yeah, we can make them and go real slow. Still not going to see them. Yeah. Much smaller than the wavelength of light. So, let's see, what number was that? 10, 11. So this velocity selector can be added to this. Let's add to our velocity selector. What if I have a velocity selector here, then the capacitor ends? Now the magnetic field continues on. Okay? And so the reason there was no bending in here is because we are balancing the magnetic force with the electrical force. But once we exit the capacitor, then what happens? Now it begins to turn, and we're back to this equation. It would have a radius that is based upon its mass, its speed, its charge, and the magnetic field. Its speed I should know at this point, right? Because its speed wouldn't have got through the velocity selector unless its speed had this ratio. And so as we'll see, when we make these in lab, we will just send out of our source electrons that have any old speed they want. We're just lucky to get free electrons. And we'll just make billions and billions of them. And some will be going fast and some will be going slow. And most of them will never make it through our velocity selector. But a small number will be going just the right speed. And those that are going the right speed, and by my definition of right speed is this, will then make it to the other side. They will then make it into the magnetic field, and they will then arc over. And they will arch around. And how much they arch over, the radius is determined then by how much their speed is and their mass. So let's say that I had a bunch of different objects down here. And when I say a bunch of different objects, let's say this is some organic chemical that I don't know what it's made out of. It's probably got a lot of carbon, it's probably got a lot of nitrogen, it's probably got a lot of oxygen in it. But I'd like to know how much. Well, I could take that molecule, I could put it in a furnace, I could get it really hot so that it bangs so hard that the oxygens and the nitrogens and the oxygens all come flying off. I could get them even hotter so the electrons come off. And then I can take all of those and send it through this. And it would bend. And the carbon, the oxygen, the nitrogen all have a different mass. So do they end up at the same spot? No. And so I put a collector. I put a collector, say, here, and I get the one with the smallest mass. Which one has smallest of nitrogen, oxygen, and carbon? So carbon. So if I put a little collecting plate right here, this should arc over, and I should get all the carbon there. I put a collecting plate there, and I should get nitrogen. I put a collecting plate there, I should get oxygen. I then weigh how much oxygen, nitrogen, and carbon I have, and don't I have the ratios between them? And so some of you are smiling, and you have done this before. What's this called? A mass spectrometer. I have separated it based on its mass. And that is a very useful tool in things like organic chemistry or in separating nuclear fuels. That's always a challenging one too. You could do the same thing with uranium. Uranium comes in two flavors, if you will. There's the heavier one, uranium-238, which is kind of useless for making nuclear energy. But then there's the lighter one, the uranium-235, which is really nice, but it comes in small packages in the earth, and it's not concentrated enough to work with anything. So how are we going to make it more concentrated? To either make nuclear energy or nuclear bombs. We send it through a mass spectrometer. And as we send it through a mass spectrometer, we put a collecting plate there, and uranium-235 lands there, and uranium-238, being a little bit heavier, lands a little bit further over, and then we can start collecting the, the 235 and just kind of get rid of the 238. Actually, it's still very valuable, so we call that depleted uranium, and it's used for other things, but the 235 is the main goal, yeah.
This seems to be more, mass spectrometry seems to be more designed for measurement and not really for separating mass. Is it possible to separate mass on the mass scale? Because it just seems to be such a long...
No, this is separating by mass.
Like, is it possible to have like a lot of it? Like, for example, you want to separate you basically have a chunk of uranium, for example, or something like, or maybe just heavy water.
Do it for a long time. I mean, isn't that the whole world politics right now? Isn't that what Iran is doing right now? And we're all questioning how long it's going to take before Iran gets enough separation, although they're not using a mass spectrometer, they're using cyclotrons.
Did you put it at a certain velocity? Is that what the centrifuging is for?
No, their process is a little different. They are not separating it this way. They are separating it with a cyclotron. So you just take them and you heat it up and you spin it. The heavier stuff goes deeper by a certain percentage. So then you move it into another spinner and it is a higher percentage, and another spinner and another spinner. And after a couple of years, you can get some heavy concentration of uranium-235. It's going to take a long time. But it can be done separating. But again, you're separating by its weight because of motion as opposed to, well, I guess this is motion too, but this is magnetic. Magnetic and electric. All right. Oh, let me keep going with this. How much time we got? Oh, good, because I want to show you. I think we can just kind of finish this and show you the last piece of all this. Where is the cathode ray tube? This is the one you were asking about. I was saying this is the beginning of a cathode ray tube. Here is kind of an elementary look at a cathode ray tube. But what I can do is back here, I can send the charges out here and then pass them through a plate that is charged this way and a magnetic field here. The idea being then that only ones that are going the correct speed would get through my velocity selector. After that, they would begin to turn, and that can be used to control where they hit on the screen. And so one of the easiest places you already saw is this cathode ray tube. How is an image formed here? And it is the control of these magnetic fields. And in this case, these magnetic fields are created by current. And so that's the next chapter we're going to get to. But by turning the current up or down, I can control where those electrons hit. And so a TV screen, at least an old-fashioned TV screen, using electrons from the back, that's why the old TVs are, thick, and they have to send the electrons from the back up to the screen. You coat the screen with some kind of material that gives off light when they are hit by the electrons. But what you can do then is control where that beam hits. And so for a TV, you can start up in the corner and scan across, hitting or not hitting, and making light or not making light a first row, and then start again. And make a second row. And make again a third row. And make again and again. And again, and the design of a picture is that we have a beam that is sweeping across. Now in this case, the TV is not hooked to anything, so the electrons just kind of hit randomly and it looks like snow on your screen. But with control, we can make an image here. And of course, if it's a colored TV, you would do this 3 times. You would have one beam making red, another beam making green, and another beam making blue, and the 3 images on top of each other is what you would see in terms of a TV. But it's just using the control of the beam with a magnetic field. That's the point here, yeah.
How can you control the color that the beam makes?
You control the color by what it hits. what material it hits. So if you look on a colored TV screen and you look real closely, you will see what they call a colored pixel. And one is red, green, and blue. And there's a different beam that hits the different one. So what I could do is only hit the red material, and that point would be red. And so if this was a picture of a woman in a red shirt like you have, well, it's too long for arms. But if she's got a red blouse or jacket like you, then the TV would only hit the red at that particular moment, and then a little bit later. But it's going to scan all the way across 525 lines, at least old TV. High definition is what, 1080? 1080, right? 1080?
4K.
So go across and do 1080 sweeps there. Yeah. Now, with that in mind, how many here I'm doing on time here? I do want you to see this again. So not only is the magnetic field used to control where the beam hits, I took this as an opportunity last time to use this magnet to show that I could deflect them. And so these electrons are supposed to come up and hit the screen, right? And then give off light. If I put a big magnet here, then again, unfortunately, I kind of block that. But what I wanted you to see is they don't hit the screen anymore. They are deflected away, except where? In the direction of the magnetic field. Because what did we learn is if the electrons are moving in the direction of the magnetic field, how much force do they have on them? 0, right? So if I extrapolate that to good old Mother Earth here, let's go back to that picture we had a few moments ago of Mother Earth. If the Earth is being bombarded with charged particles from outer space, which most of ours come from the sun, so the sun is having these massive nuclear explosions with charged particles racing at us and all the way through space, we call that the solar wind. What will happen is if they come across from the sun and try to hit the Earth, they get deflected. Now, they're going in all kinds of crazy directions, hitting each other. Is it possible for them once in a while to hit the Earth? How would they hit the Earth? And the picture back in 29 probably shows it best. Didn't we learn that the motion in a magnetic field would be a helix? Wouldn't they be circles around the magnetic field? And so all these charged particles that come in from the cosmos here, or from the sun, they're going to hit and they're going to wrap around, they're going to follow the magnetic field. So where are they most likely to hit? Either in the North Pole or the South Pole. And then what happens when these charged particles hit something? They give off light. And so if you can imagine, these charges will come in, and near the North Pole there would be this ring up in the sky of lights. The picture I found this morning was actually pretty good here. Where's my computer? Where's my drive? Oh, I thought I brought my drive. I didn't put it in. I don't know what I did with my drive. Oh well. I guess I won't show you, but I'll show you one more then. Bummer. Is I wanted to show you a nice picture. Maybe I'll start that one next time. But just in case you missed the idea, here makes a good experiment of what happens if I make charged particles bouncing off of here and hitting something. And so, it's not going to make a spark. Yeah, maybe we're not going to see that either today. Ah, there's a spark. Okay. Come on, spark. Yeah. Did you see it? Ah, there we go. Can you see a little flash anyways? Maybe that's the best we're going to get today. Turn off the TV? Oh, okay. And then likewise, it should make quite a bit of a magnetic and electric field. So hopefully it'll foul that up as well. But yeah, so there's your idea of your northern lights. And your TV, when they hit a material, they're going to give off some light, depending on how that material is set up. Well, good. We've about finished the chapter. Now we need to do some examples, so that's what we'll do next time.
Go to the lab, right?